Good afternoon, everyone, and welcome to the School Physics Educators Forum. And thank you for taking your time off on a Sunday to join us for this discussion. As I've already mentioned, this is being recorded, and we will make this available on the forum's YouTube channel maybe a week or 10 days from now. My name is Anand. I was a school teacher like all of you. For about 15 years until very recently. 5 months back, I moved out. Now, in our forum, we don't stand too much on formalities in these sessions, but we would like to give you some context and a quick introduction about the forum and the kind of work that we do. I'd like to mention 3 people who are very instrumental in initiating and sustaining this forum. Professor H.S. Mani. I don't think he's joined. He said he will join in another 15-20 minutes or so. And in a way, I'm glad he's not here because he doesn't like to be talked about his credentials, which I will tell you in just a bit. He had sent a message in the group saying that, hello, I am Mani, I'm interested in physics, and I'm Anand's friend is what he had said. But what he did not say is that he's an adjunct professor at CMI, Chennai Mathematical Institute. He was professor at IIT Kanpur. He was director of Harishchandra Institute in Allahabad. And he's a very accomplished researcher and a physicist. But more than all this for me, he's 50 years older than I am, right? And he's still so enthusiastic about meeting new teachers, about helping them with physics, with popularizing science, meeting students, and he's been such an inspiration. And this forum was the result of a conversation that Professor Mani and I had about, I think 2017, right? And he's been a dear friend all this while. Anytime I have a doubt, I can call him and clarify. He's been such a lot of help. And therefore, when we founded this, the whole point was that if we want to improve school education, the only way to do that is to empower teachers. And that is how we got started, and that is why we are doing what we do. Now, the second person is Dr. Jayashree Namdas. I don't know, Jayashree ma'am, if you're here, but I'll introduce her as she was former director of Homi Bhabha Center for Science Education. And her work in science education was probably the first of its kind in India. The thesis that she did is, from my understanding, and she was also a Mani sir student. So, closely knit, and she was there with us from the very beginning, the very first meeting when we had, in-person sessions. She had come and she's always been a great support. Last but not least, Miss Sudha Balan. She's the principal of NPS International in Chennai, where Nila works at the moment. I worked there for a year, and she is the one who kind of sowed the seeds for this forum. And when I was working there, and I'm grateful for her. The timely support that she gave, the many ideas that she gave, the conversations that we had. I mean, it's strange that it's unheard of that a person who's not a science teacher and who's not to be so interested in science and to push people so much into science. It's quite something. So we're grateful to her. She in the first in-person meetings that we have, many of it was in NPS International, and she's the one who talked to me about this whole sharing of knowledge with the larger community of teachers. So from 2018, we had many in-person sessions with teachers in Chennai initially. That's where we started, and this time the concept of online sessions were rather alien. Then during the pandemic, we expanded in a big way and had many teachers from all over India join the forum, which we started including more disciplines. Now we have a full-fledged chemistry group, very enthusiastic, and they just finished their online sessions last month. So now it's our turn. Now, what way we function, we are purely voluntary. The only capital involved in running this forum is the will of like-minded educators such as yourself, the love that we have for our subject, and the excitement that we want to share with the students that we teach. So if you have ideas in teaching and learning, and if you would like to share your experience with a larger community of teachers, do come forward, get in touch with us, and we will be happy to organize online sessions so that you can interact with a larger audience. So this is very central to today as we move on. Now, there's no cost involved in conducting these sessions except this Zoom license that we have to get. And we've been helped by Chennai Mathematical Institute and National Academy of Sciences through Professor Mani till last year. This time around, we are being helped by Azim Premji University. It's where I work now, and the Azim Premji Foundation, which under which the university is established, has been working with. Yeah, sorry about that. Not many people know about it. And the university is focused on this concept of education for social change. That is in fact, that's the motto of the university. So many thanks to Azim Premji University for helping out in this session. So that's it as far as introductions are concerned. I'm fully aware how busy school teachers are. And Sunday is probably the only day that you get off, and yet you have all shown up, and which can only mean how much importance you give to the work that you do. Now, whether you see it or not, this positive attitude that you radiate has a considerable impact on the education of our country, and I cannot stress that enough. Thank you again for joining. I sent out about I think 300 emails. 300 to 300 individuals, and contacted 300 people directly over WhatsApp. And what's the number now? We have 54. That's so I think that's a great number. So thank you, all of you, for joining. Right. So the topic today is I had mentioned, as I mentioned in the emails and WhatsApp, is a visual way of learning waves and oscillation. The topic, when I wrote it down, actually I had put it down as a visual way of teaching waves and oscillations. But then I realized that I have learned more from this than I have taught it this way. So I thought it's the best way of putting it was, a visual way of learning. Now, and I had many people ask me, is this for an ICSE board? Is this for the CBSE board? Is this for senior school? So my answer was very clear. Irrespective of your school affiliation, the syllabus you're part of, the class that you teach, I'm fairly confident that all physics teachers and maybe even some maths teachers will have something to learn from this, right? So I'm going to go ahead and keep everything very basic, and then we'll slowly build on and make it more complex. Right? Thank you. Right now, this waves and oscillations is difficult because it's a phenomenon that takes place in time. So something that is dynamic, it is almost impossible to represent this inside a textbook. Unless we have one of those Harry Potter style books where you open and you see these things moving. You can't really teach this in an effect. I mean, students get confused, and it would require that the students use a lot of imagination to get insight. So, which is where I stumbled upon what we are about to see. So let's start with this. Now, could you tell me what these equations mean? I'm not going to. So this is the whole layout. You have a graph here, and you can type your equations here. Y is equal to mx. That, like I said, I'm going to keep it very simple, right? And just tell me what this equation means. Let's make this interactive. You can just unmute and just speak.
Yeah, it's equation of line. Y is equal to mx. Straight line.
What is m and what is c?
M is the slope, the gradient.
Yeah.
C is the y-intercept.
All right, great. That's correct. So what I'm going to do is, you will see as I'm using the software, you'll also see how I will also give an introduction as to how to use the software. So let's put in an equation. Let's put 2x plus 1 and press enter and see the line comes here, as you can see. Now, if you want to teach a student about, again, when we start, we don't have much to do with waves and oscillations. We will slowly build, right? Now, if I copy that here and I change that slope value to 3, and then you will see that this is the black one and this is the red one, and you will see that the one with slope 3 has a higher slope, as you can imagine. If you want one with a lower slope, you can just give y is equal to x plus 1. So you see this color is not the best. You go to settings and I can change the color to something else. There you go. So this you can see. But the best part here is that instead of going one by one with equations, I can just type a generic equation, mx plus c. Okay. And let me just close these. I don't need these anymore. So if you ask yourself, what happens to this line when you change m? You have, in fact, if you close it, when you type it itself, it'll ask if you want to add a slider. And then if you give all, it will show you the slider, and the m at the moment is 1, and you know what to do with slider. So when you increase or decrease, you see how the line changes. So instead of having 2 or 3, equations parallelly written to compare, you can just have a single equation and you can just go back and forth. You can go to negative slope also if you want to show how it works. Now, what about c? What happens when you change c? As you know, c is what we call as the y-intercept, that is the value of y when x equal to 0. So in this equation, if I zoom this in a bit more, you can see. In this equation, if you put x equal to 0, you get y is equal to c. So that is 1. So it goes through the point 0, 1. So if you change that, as you can see, the intercept will go up or down. That's the way it works, right? Now let's take another equation. Ax square plus bx plus c, right? Now just zoom out a bit. It's a parabola, equation for a parabola. So this m is not here, so I'll close that. But I still have, so let's go to c equals 0 and b equal to 0, and then we'll ask the question a is equal to 1. So what happens if you change the value of a? A is this the coefficient of x squared. So if you put a is equal to 0, it goes and becomes a flat line. So a is 0, b 0, c 0, so y equal to 0, and that's the x-axis. So as you increase a, it gets more curvy, so to speak, right? Now, if you increase c, c again is the y-intercept. So if you increase the value of c, the y-intercept changes. Now the question is, can somebody tell me what happens when I change b? To give you a clue, I'm going to make, I'm going to make a straight line here. Maybe now you can tell me. Maybe now you can, for this one there, you can, I suppose you can, do it and see what happens. Okay, so I'll go ahead. So B changes the slope of this blue line, right? This blue line, the B value will change the slope of the line at the intercept here. So look, can you see that? Which is why I gave this black line to show you that that's the intercept. And wherever you go, so, look very carefully, the slope at that point changes as you change the value of B, right? And if you want to change C, as you can see, it goes this way, that way, right? The value, and if you want to see what happens to the graph, without the line, you can see this. That's what it does. Can you see that the y-intercept, this B is the slope of this curve at the y-intercept. That's the idea. Okay. All right. Okay. So moving ahead, now I want to ask you, we'll step into, what do you say, waves and oscillations. Okay, we'll go ahead. So now let me ask you a question. The equation for y, for simple harmonic oscillation is y equals a sine of, I don't have an omega, so I'm going to put w and t, and then I will just press enter. And you see, when you put y is equal to a sine omega t, and we plot a graph of y versus t, then you get that graph that you're very familiar with. But here, you're not getting that. You get a straight line. Because you see the graph is a graph of x versus y, I mean rather y versus x, right? So there is no x in this particular equation. So instead of t, if I make it x, then you will get the graph that you are familiar with. Okay, but just hang on. Let me go back to using t because I want to use the t for something. Right now, this is an infinitely long line, as you can see. I'm going to zoom in to here, and here comes the best part of using this software, where like you saw in the value of changing the value of intercept and slope and so on. Here I'm going to change the value of t, and best part is you can just, there is this button here called animate, and you click on that, and then you see what I don't know if how smooth your the video rendering is, but if you look very carefully, it's this line executing simple harmonic oscillation up and down. Right, and with this value of omega, it's at 1 now. I'm going to reduce it so you can see. You can actually change the range here for the slider. So I'm going to click on this 10, make that 0, and I'll just make this say 2, 0 to 2 omega value. So now if I reduce the frequency, you will see that rather clearly that it is oscillating about. Oh, I'm sorry, let me just change that. 1 second. Right. This animation is there. This animation mode, you can put it in different ways. You can have it go forward and then backward. You can go forward all the way to the end of the range and then come back and start again. And there are options like this. You can speed it up, slow it down, however you want. So I'll let you explore that, and we will be meddling with it quite a bit. So I'm going to put t values at 0 and to 10, right? And then let's see what happens. So we start here from 0, goes all the way to that end, and then comes back. You see, the time is not, it's not enough for it to get all the way across. So I'm going to now make this 40, and then let's see what happens. I think it'll go all the way down and then back and all the way up and then back. One full oscillation. Right? Yeah, actually, a little more than a full oscillation. If you slow this down, you can see that, right? Now, can anybody tell me? So I'm going to watch this. Huh? You start here at the middle. It goes all the way to 1. It goes to 1 because our amplitude value is set as 1. If you set it to 2, it will go all the way to 2. There you go. And I can zoom out a little bit, right? And watch that. So it goes from the center all the way to the end, and then it comes down all the way to -2 somewhere here, and then it goes all the way to the other end again, and then comes back, and then somewhere here our time, we run out of the time here, so it steps down. So you can actually, so this is literally what simple harmonic oscillation is. The problem is when you write this equation, very often the students misinterpret y is equal to a sine omega t, meaning a function of, in fact, I'll write if you have the equation y equals a sine of omega t, this is what we write as y of t, meaning y being a function of t. On the other hand, if you write y is equal to a sine of some constant into x, this now will become y is a function of x. So you see, when we start teaching simple harmonic oscillation, we use this equation. But the graph that we give for this is this graph. And there is a confusion in the sense that between what really happens and what this looks like. Right, this is y versus t, and children very often confuse this t and this x because anytime we draw a graph, we use y and x here, right? So this is one of the confusions that I have found over the years that children come up. So the point, in fact, this is the reason why this topic is difficult. Like I said in the beginning, it's something, you put something like this. I know this is very crude. My drawings will never be, which is why I use the software to start with, right? So
sorry, Anand.
Yes.
Is the graph what you are drawing first? Are you meant to say that the graph is in between the position and time graph? That
So
means
this, for what we are discussing now, let me clarify. What we are discussing now is y equals a sine of omega t, where this is very clear that it is a function of time. It's not a function of space.
so the variant y with time.
Hmm.
Do I understand correctly?
This is how a single particle will move as time goes by, which is what this is showing. This is, I know this is a line, but you just give me some time. I will make it into a particle. That's what this whole thing is about. So just give me some time. Bear with me. Let's put this together. Yeah. Thanks for carrying. Okay. So now I want to ask you. We'll come to the. I'll just close all this and then let me just supposing I want to take a straight line equation again. Let's take. I think I had written down. We also know the equation for a wave, which is y equals a sine of omega t minus kx. Okay, we know that this is the equation for a wave, and you know, you don't have to use much of a brain to figure out what will happen if I animate t. Now, that's what happens. This is going back and forth because that's how, if I give it like this, it'll keep going forward. Hold on, let me change these values back to, I don't know, 20. And now if I animate, it'll go forward, right? This is what we call as a wave. This is the standard wave equation. But you know, it's given, and you know, there are parallel. I'm not happy with this. I want to break this down, which is the whole purpose of this session. I want to break this down into real small bits. Okay, so if you just to see how this goes, if you increase the amplitude, as you can imagine, the amplitude goes up, right? If you have difficulty watching this, I could just change the thickness of this line to slightly bigger and make this one. Okay, I think that should, and make it, or green color. Yeah, I think that should be okay. There you go. So this is what's happening. Amplitude, I'll bring it down. Now, if I change the frequency, the angular frequency rather in this case, let me move it to just 1 and keep it. So if I reduce the angular frequency, you will see that it moves a lot slowly. Let's see, this one is moving very slowly, right? You increase the angular frequency, it moves much faster, right? Now, I don't want to go into this K just at the moment. K has to do with the wave. Okay, well, while we are at it, has to do with the wavelength. The larger the value of K, which is, I think it's called the propagation constant, right? The larger the value of K, the shorter the wavelength. In fact, I can write that down. We already know the equations, which would be y equal to a into sine of, well, I put kx first, it doesn't matter, kx minus omega t. And in this, the value of omega, as you know, is 2 pi by the time period. And the value of k, the propagation constant, is 2 pi by the wavelength lambda, right? So if you rewrite this as 2 pi by lambda into x minus 2 pi by t into t. Right, and of course, if you take 2 pi out of this equation, I'm sorry, this term, you get x by lambda minus t by capital T. Now, this gives you a sense, because you see what now is going on is, what are we measuring finally here? This now is an equation of y of x comma t, and there's no way you can show this in a textbook. What you can show in a textbook will be y of x comma at position at t is equal to 0, then another diagram for x at x is equal to 1 second, and then another diagram for x equal to at 2 seconds, and so on. And for each of these, you will see that the wave is moving forward and forward and forward. Right? That's the best that you can do on a textbook. Right? Now, on the other hand, if you take the calculator, let me just adjust the wavelength a little bit more. Right? And then you can see as the value of t changes, what happens? What happens? Well, just animate it. It shows that what's really going on. And in this particular case, this is not a single particle that is doing like this. This is an entire, it's a 2D thing, in the sense that actually it's 3D, in the sense 2 dimensions in space and 1 dimension in time, in the sense that you have X and Y, which I can show you here. This is literally, you have a string, and then, if you can hold it here and jerk it, and you will get it to take the shape. That is literally what this equation means. X equal to a sine of kx minus omega t. Now, when I started teaching this caused considerable amount of problems for me. I didn't understand what this thing is all about. So, which is exactly where which is exactly what I would like to address today, right? So, how I'm going to do that is as follows. I'm going to close all of this, and I'm going to start with a very simple example. Now, you can help me here. Y is equal to x. It is a straight line at 45 degrees passing through the origin. Now, y equals x plus 1. Then, instead of x plus 1, let me do minus 1. Huh? Give me a second. Do minus 1. Right? Then I'm going to write y equals x minus 2. Then I'm going to watch what's happening as I type, and you see the pattern in which I'm typing. Y equals x minus 3. Y equals x minus 4. Right? As you see this, in a manner of speaking, you can see this. It's, if I go one by one, it's first this one, then the line moves forward a little bit, then forward a little bit more, little bit more, little bit more. And you don't like this, you want 2.5, put 2.5. You see that the line will accordingly adjust a little bit, right? Yeah, I was just giving 1, 2, 3 cute values so that it's easier to understand, right? Now, so this is the point that I'm trying to make here. This x value here, look at that. Now, instead of putting it separately, I'm just going to put y equals x minus, say, well, you can use any variable. I'm going to call it a, right? And I add a slider there, right? I'm going to switch off all these ones. I don't want to see that now. This is the equation. And I'm going to change the range. I'll start at 0 and go, say, all the way to 5, because 5 is what I see on the screen, right? As you can imagine, you put a 0, you get this first equation, same. This moves forward. When a equal to 1, you get the second equation. There you go. So 0 to 1 goes from here all the way there. Then when I come to 2, it goes from here to here to here, and 3 here to here to here, 4 here to here to here. This is the idea. Okay. I'm sorry. Can you give me 1 minute? Yeah. Sorry about that. So it keeps moving forward. Now, what I'm trying to say is, you don't need all these equations. You just need this one, and you can animate this forward. So this is literally what I use. So I don't want to use I want to use t, because then I represent it as time, right? And so in a way, what I'm trying to say is, let me change. Every time you put a new variable, you have to define the range. It's a little bit annoying, but for what it's worth. So you start here. It means I could say that after 1 second, it will be here when t is equal to 1. After 2 seconds, it is here when t is equal to 2. After 3 seconds, it is here when t is equal to 3, and so on, which is represented separately with this, and this, right? These 4 graphs. Now, I don't use this. I use only this, right? And when I play it, you'll see it just moves all the way, and it goes out of the screen because it has to go all the way to 10 there. That's why. So this is going to be a first point that you have to remember, right? If you want to, 2 things to take from this. Number 1, if you want to off a graph, any graph, any shape that you want, right? Any graph, any shape that you want. We started with, it applies to any shape, any graph that you want, but we just take the simple case so that we understand how the thing works. So if you take this this a graph of y is equal to x, and you replace in this graph, you replace x with x minus t, right? If you replace x with, what did I say? Replace x with x minus t, right? Then you get this equation in this particular case, of course, when you substitute this here, replace it here, and then as t changes, you can interpret this as the graph moving along positive x axis. Okay, it moves along the, you can say that the graph moves towards the positive x. You can interpret it as something else. That is, you can rewrite this equation, this very equation, and you can call this as x equal to y plus t, right? And then you can interpret it in a different way and say that, oh, this is the same as the graph going downwards the y-axis. In fact, I'll show you that. There are two ways of interpreting this, but I want to stick to just one. Now, how do I show you that? Hold on. I will just keep this, and I want to say y. I want the y value. Okay, let me put this here. No, I'll add it here. I'm going to, this is another trick when it comes to using the software. So y, if you give y is equal to 2, it gives you that line at y is equal to 2. But on the other hand, if you say y is less than 2, it will shade the area for you. If you give y greater than 2, it will shade the area above it with dotted lines. Because it's greater, it won't take that line. So if you give greater than or equal to, you will get a solid line there. Watch, I'm going to put equal to now. Can you see, get a solid line, right? Greater than or equal to 2. The y can take those values. Now I'm going to put y less than, less than or equal to 2. Oh, minus 2, sorry, minus 2. And now I'm going to make this, I don't like this. I want to make this, I'm going to change the transparency of it. This is the transparency. If you put 1 means it will be a solid line. Oh, I think, wait, hold on. This is the opacity. And if I put here and put this as 1, there. Now watch. Now watch. If I play on T, it looks like the line is moving forward. Okay, the line is moving forward. Surely the line, this is coming back because I put the animation on up and forward and backward. If I put the animation going that way and then repeat itself, this is what you'll see. You see the line going forward. But for the same equation, now I'm going to now give x greater than or equal to 2 and y, x less than or equal to 2. Oh, not 2 again, minus 2, sorry. So, and then I will switch these two off, and I will change the opacity of this to make it dark. And this also I will make it dark. Mind you, it was the same line. There was no difference. I didn't change the line. It was the same line. There. If you want the other one, it's the same line. I will zoom out a little bit. This is what we saw. When you play it, it moves forward along the positive x-axis, right? It goes towards the positive x-axis. The same graph can be interpreted as going down the y-axis also. It's perspective. And what this really then means is that this equation can be written in two different ways. One being this way and one being this way. These are the same equation, these two, as you can see. But we are going to look at only one of the interpretations for now, okay? Which is, if you have an equation, in this case, you have y equal to x. This, by the way, I will show you that this works for any equation, right? But I want to take only this equation because it's simple, and then we can make it more and more complex. If you replace x with x minus t, I'm going to go one step ahead. And if you apply your physics now, and if y is in meters and x is also in meters and t is in seconds, then you will see that this line is moving forward in the x axis, 1 point in every second, or in other words, you can call it 1 meter per second. Right? It's moving forward along the x-y. Look at that. Look at the equation. I'm going to replace this x minus t. So what happens? Y at y is equal to x at when initially it was at 0. When t is equal to 0, you get the equation y is equal to x. It passes through the origin. At t is equal to 1, if I call there, I say 1 second, then you have y is equal to x minus 1, and then you see that the line has moved forward to 1. Let's see that. Let's see that. Let's see that. And I don't want to use this perspective. I'll use this perspective instead. So let's check that out. So t is equal to 0, and it's easier for me if I give steps here. I'll give 0.5, right? And watch. So at t is equal to 0, y is equal to x. At 0.5, it moves forward 0.5. At 1, it moves forward to point this 1. It passes the x-axis at 0.1. Now, this is what all the points here are doing. So you can then very happily, you can say that in 1 second, it moves forward. If this were 1 meter, you can say in 1 second, it moves forward 1 meter. In 2, because all the points are moving forward by the same amount. Otherwise, if for this line, if some lines move, some points move a little faster than the other, then it won't remain a straight line anymore. It starts to curve around, right? So as again from 0, it moves forward. Now this is because it is moving at the rate of 1. If we use the unit meter here, 1 meter per second. Now, if you want to go at 2 meters per second, make this 2t, right? Now watch, after 1 second, it is moved 2 forward. After 2 seconds, it is moved to 4. After 4 seconds, it's moved to 8. It's doubled its speed, right? I don't want to go in and write what is 3. Instead, I'll just put a generic value here, v, as in velocity. Now I can choose the velocity. If my velocity is 1, it will move forward at the rate of 1 meter per second. My velocity is 2, it will move at the rate of 2 meters per second. It goes out of the window, I'm sorry, right? All the way. And then if I move it forward to 3, it goes at the rate of 3 meters per second, right? You can check it if you want. See, at 5 seconds, it has gone, v into t will be 3 into 5, 15. There you go. It's at 15, right? And mind you, this point here on top, was originally, if you click on this, it will show you this point. That is 16,1. So this point at t is equal to 0, where was it? It was at 1,1. So you see, it's moved forward 15 points. This one was at 0, 0, moved forward 15 points. This one is at -1, -1. It has moved forward along the x-axis 15 units. That's the idea, right? Let's check that. 1, 2, 3, 4, 5. Right? Wait, let me check. What was the point again? This was -1, and -1 plus 15 would give you 14. So plus 5, and then go here and check there. It's at 14. So all points are moving forward at the same rate, so to speak. So this is our starting point to understand how this is going to work. Okay. So I'm going to reiterate this once more so that you understand. This works for any graph. For any graph, if you want it to move in the positive x-axis, you want to replace x with x minus vt. If you do that, then it will move along positive x-axis with velocity 3 units. Well, I'll have to write 3 units per unit, but let me just stick to 3 meters per second. Right? Okay. This is our starting point. Now, if you wanted to move along the negative x-axis, you don't replace it with x equals x to x minus vt. Instead, you replace it with x with x plus vt. As you can imagine, if this value of v takes a negative value, where is the v here? Let me go back. Oops. Okay, here we are. So now this is positive. This is positive, so it moves along the positive direction. And now let me take off these steps out, keep it smooth. Right? And now if I move to the negative, go to t t0, go to the negative, give -1. That means v is -1, because then, which means that the equation has now become y equals x plus vt, because v value is minus. And then you play, it goes along the negative x-axis. Is that okay? Is that okay? Right? Any questions till now? Anybody? All right. Okay. I will go ahead now, and I will reach the what I finally wanted to talk about. So this can be now logically extrapolated, in the sense that if you want a graph moves along positive x-axis with velocity, this one, if you replace x with x minus vt. If you replace x with x plus vt, it goes along the negative x-axis. And it's only a logical conclusion that if you replace the y with y minus vt, right, y minus vt, then it moves along the positive y direction, y-axis. And if you replace y with y plus vt, it will move along the negative y-axis. Okay, and this is true for, what did I say, for all graphs? Let me show you. So I'm going to take an equation. Let me just, what is the equation for a circle? Can somebody help? Anyone have some participation going?
I think that x square plus y square is equal to a square.
X square, thank you. X square plus y square. I'm going to put it as a r square, because then r is then the radius. And there you go, you get a circle. It's beautiful. I love the software. It gives you a beautiful circle. Oh, by the way, I want to ask you, you know the equation for a circle. Do you know the equation for a square? Interesting thing, I came across this short video on YouTube where somebody told me, this guy was explaining. It was just a mind, I just never thought of it. It was so beautiful. I will tell you. Can anybody guess? It's very similar to this. I mean, I don't think I don't think anyone will guess, but let's just do this. Instead of this 2, let me call this A, okay? Let's call this A. Oh, sorry. Oh, A. Right. So so if A is equal to 2, you get a circle. Now, if you change the value of A, if something very interesting happens, and it goes beyond the limits of the software also. I tried it. Let me just put this as 100, okay? Now see what happens as I change the value. Oh, and by the way, I want to put steps of 2 because it will work only for even values. Odd values, it doesn't work. Watch. As you go ahead, it becomes more and more of a square. So much so this guy says that the equation for a square is a to the power infinity plus y to the power infinity is r square, right? Yeah, and if you can see this, it says this equation may contain fine details that has been fully resolved. Okay, it goes beyond the, I think it goes to about 54. I think there's no problem. There you go. That's a nice square, huh? So much. So then the intriguing question then is what happens at odd values. You want to ask what happens at odd values. So let's change the, I don't want to go, I want to go by one step. So watch. I know that it goes only till 54, so I'm just going to put it as 50. So this is A is equal to 0, there's nothing, right? 1 is simply x plus y equal to r square. 2, circle. 3, I don't know what this is. 4, 5, 6, 7. Actually, let's animate it. Watch. Can you see the edges becoming sharper and sharper, so to speak? Let's play it from the beginning again. The edges get, so for every what do you say, odd value, it's not a closed loop, it's an infinitely long loop. Can you see odd values? It goes 11, 13, 15, 17, and so on. So this was a fun thing that I learned when I was preparing for this. Okay, so we'll just stick to our a square plus y squared. Oops. You want to get good to put a power, you have to put shift 6, which is the caret symbol, and then it goes up. Press shift and 6, you get that caret symbol or cap or whatever you call it. That is to the power. Okay. So I get this equation. So what did we say? I said any graph you wanted to move in the positive x-axis, you replace what? You replace x. Okay, let's be here. I'm going to copy this and make another one for comparison. And yeah, let that be there. And I will the x. I'll put a bracket so it's easier for me to work. What did I say? If I want to make it move along the positive x-axis, I replace x with x minus vt, right? And then hold on. Let me give the time steps here. And then I play. There you go. It moves along the x-axis forward. Right? It comes back because the animation is set like that. If I say it only moves forward, then there you go. It moves in the positive x-axis. It moves in the positive x-axis. Right? Okay, stop. If you want it to move in the negative x-axis, you put this as you change the value of v. You can make it there instead of going forward, you can get it to go backwards. There you go. Because the value of v now changed, which means that now this would become plus vt. That's the idea. Now this would apply. This would apply that if you now want this to also move, not also move. Let me stop this. Move this up. Then I can move this down, and then I want to let's make another one. Oh yeah, no, I'll take this. Let's make another one, right? And I want it to move in the y-axis, so I will replace y with y minus vt, right? And play, it goes. Oh, this is because now that the blue circle, which is the x, is going in the negative x direction, right? Oh, a value of v is negative, sorry, and make it back to positive. There you go. You see two of them going because the blue one we had set, I can switch that off. So now you can just see the x, the y, this one, where it's going along the positive y-axis, right? And the other one was going along the positive x-axis, right? Now, if you want to make one circle go through both along the x-axis and the y-axis at the same time, then of course you have to change the x with x minus vt and the y with y minus vt, and you get something. Can anybody tell me how this is going to move now? Can anyone tell me how this is going to move? Let me just make these 0 and 2. Can anyone help? Of course, you want to change the radius of the circle, you can do that here with this slider. Can anyone help and tell me what's going to be, how it will move? If I make it to go in the positive x-axis and along the negative positive y-axis at the same time, how will this circle move now?
Shouldn't it move through the diagonal along the origin?
Yeah. So at how?
Means 45-degree angle. It's a
45.
vector.
That's it. That's it. There you go. There you go. It goes beautifully along the diagonal. 45 degrees. If you want to confirm, you can put y is equal to x. You know that it goes along that line. Right? Right? You see that? By the way, why am I doing all this? This is now, I will slowly lead this. This is so that you understand how to do the final product. You know, we have only started with one kind of motion. We'll get into different kinds of motion and how to tweak your equation in order to get the different kinds of motion. This is only moving with constant velocity along a straight line, right? We have other kind. We can accelerate this. You know, we can get it to execute simple harmonic. How would we do that? So remember, when we had y, I'll take the simplest equation again here, y equal to x, and when we wanted to move this forward, we gave y is equal to x minus 1, which means what we are doing is we are offsetting. Offset means you move it forward along the x-axis by 1. If you put y is equal to x minus 2, you offset it even further to 2. If you want to offset it along the y-axis, you want to replace the y with y minus 1. right? Right, y minus 2 and so on. This will make this equation, meaning if you have the axis like this, the first one will be like this, the second one is forward, the third one is move forward. Okay, and I'll use another color for this. For this one, what happens? It's like this. Oh, sorry. This is x and y. The equation was originally passed through the origin. The first one, that is y is equal to x. And then if you change the y value by -1, you offset it, it goes up, so to speak. Yeah, right. This is the offset. That is what we are doing is changing position. We are changing position, right? How do we change position? Replace the x with where you want it positioned in your equation. Whatever your equation, you change the x with x minus 5, it will go and sit in the positive 5. So look at this. Let's go back and look at the ball, right? Close all this, right? Actually, let that be there. I don't want to disturb that. If I put, I will copy this. That's the Control C and Control V. And if I replace x with x minus 5, oops, minus 5, and y, I leave it as it is. If you go zoom in, can you see? Now it has moved this point here at the center, that is 5. If this was 0, it would be, oops, yeah, there. X minus 0, the center will be at 0. X minus 1, the center will be at 1. X minus 2, the center will be at 2. X minus 3, center, and so on. Right? You want to do that along the y-axis. Oh, you wanted to go in the negative x direction. You don't put minus x, you put plus 1. Okay, or 2, or 3, or 4. Keeps moving forward. Okay. What you can do the same thing in y. Y minus 1 means it will move up. Y minus 2, it will move even further. Right? Y minus minus 3, it goes even up. Plus, it goes down. Plus 1 goes down. Plus 2 goes down further. Plus 3 goes down even more. Right? And if you want to animate this, just give a general thing as A, and then you can just choose your value. Then it will just go up or down as it pleases. Right? This is to fix the position of your thing. In this place, I've drawn a ball, and I want this ball to be at 0. I will put the value at 0, A as 0. So I'll get my original circle equation. If I wanted to move up above towards the positive y-axis, I replace the y with y. I add, I subtract. If I wanted to move up, I subtract by how much I wanted to move. Put 1, it goes up. So this is about positions. Now we also saw, so I'll take the original equation that we were using, y equal to x. So if you want to change position, replace x with x minus a along the plus axis, plus a along the minus axis, and similarly with y also. Right? If you want it to move, you replace x with x minus vt. If you look very carefully, you are basically doing the same thing. Only in this particular equation that a is in meters. In this particular equation, v is meter per second and t is in second and cancel to give you meters. So together your v times t becomes the offset position. And since the t is changing, it keeps moving forward. That's the way it works. Right? Now, who can tell me if I wanted to accelerate along the positive x-axis, how will I change? Of course, if you're going along the x-axis, you have to change the value of x. How would you replace? So this is position. This is a constant velocity. Right? Now, if you want this now to move with a constant acceleration, how will you replace x with what? It has to be x with x minus something. If you want it to go along the positive x-axis, what will you replace it with? Can anyone guess? It's very easy. Okay, I'll give a clue. You have s equals what we were seeing till now when it moves with a constant.
AT square.
With AT square?
Yes, sir.
X minus
AT square.
Yeah. You're right, but I would like to get a little more precise about this, because ut was what we did so far. It's simply
So half AT square?
correct. So because why half AT square? Because then we can call A as the acceleration, and we can define A. If it is 1, it will move at the rate of 1 meter per second square forward, right? So see how this happens. Huh? We originally wrote S equal to not UT, we wrote VT. I agree, we wrote VT. Let's just imagine it's UT for now. And this is what we teach them in lower classes and say that, see, the object is moving with a constant speed in a straight line. When it accelerates, you have an added term here. So if you replace x with x minus ut, it moves with a constant speed. If you replace x with x, well, minus of ut plus half at square, what do you think will happen? Well, it will start off with an initial velocity u, and it will accelerate at the rate of a. Yeah, this is a little difficult to show because it runs out of your screen so fast, right? You have to. So what I will do, therefore, let me go back. I hope that is clear. Does anybody want that explained once more? I'll be more than happy to do that. Right? I want to call this u minus, and then I'll put another bracket inside because then it's easier for me. Minus ut plus half of a t square. Right? There you go. You got all the sliders you want. So I'm going to put first. Okay, I presume you can see my screen. So as I was saying, yeah, I want to, instead of calling it equal to r square, I'll put it less than, because less than or equal to, so then it will color it very nicely. I will go to the settings. I will change the opacity, make it 1. I'll keep it black in color so we can spot it very nice. Right. So now let me put u as 0. First, I'll put change. I have to, every time you have to change these ranges, so it becomes rather annoying. T also, I would like to go it forward. So I start from 0 time to say 10 seconds, right? Acceleration, there's no way I can get 10 and all. I'll keep this as, I'll keep this there from -2 to +2. See something interesting. And R is, of course, the size of this thing. So you can change the size to get your, so I'll keep this at 0 to say 3. That should do it for now. And I will keep it as in steps of 1. Okay. So I'll get 2 discrete values. All right. And t is 0, a is 0, and t is equal to u is equal to 0. Well, you can play, if u is 0 and acceleration is 0, you can play time all you want. The ball is not going to move. Nothing will happen. Right? If you want it to move, animation to both sides, not forward and backward. That way we have no confusion. Nothing will happen when time goes by. Now, if you give it a slight velocity, it will move. It's very subtle. Let me increase the speed to 1. There you go. It will move. Now, okay, this we have already seen. Now I'll bring the u back to 0. That means this term here is 0. You're only going to give it acceleration. Let me give it a small acceleration. I don't know how fast this will go. So now watch very carefully and see if you can spot the acceleration. Huh? Can you spot the acceleration? Can you spot the acceleration? 0.75 meters per second square. Can you? If you really want to spot it, yeah, if you really want to spot it, you want to start with a negative velocity and see if something very interesting will happen. Huh? Watch. Wait. Let me, hold on. Oops. Hold on. Let me start with a negative velocity. Time t is equal to 0. I will start with a -1 velocity and I will slowly let it accelerate. That means the object is actually going along the negative x-axis, but it's being accelerated in the positive x-axis. So play, watch, it will go back. Oh, that's very subtle. Oh, I'm sorry, I'm playing the wrong button. Sorry, I was supposed to play. Oh, let me keep it there. Press the wrong button. T, watch. So it goes this way and then it turns and goes back. Can you see that? Can you see that? Actually, I can make it a little more obvious here now. here. There you go. It's going this way, but because of the acceleration, it turns, stops, and then goes along this. It's not enough. Time is not enough for it. So let me give it some more acceleration. Huh? And time t is equal to 0. I will get it this one. Watch. It will go along the negative y and then turn around, and you can see it accelerate there. There, you can see it accelerate. Is that okay? So now you tell me. So if you want to move the position, you replace x with x minus s. If you want velocity, constant velocity, you replace x with x minus ut, actually in a bracket. If you want constant velocity plus constant acceleration would do, no? Constant acceleration, then you replace x with x minus ut plus half a t square. Now it's only a logical step now. If you want this ball to execute simple harmonic oscillation, how will you replace along the x-axis? How will you replace the x? X with what? Anyone? It's a very logical step. What is the equation? See, this is the equation. You want to change the position, you minus that position. You want to change the velocity, minus u times t, right? Here minus ut. I hope, I think we are clear in this fact that in all this, ut dimensionally, x dimensionally is meters, ut dimensionally is meters, half a t square is also meters, right? I mean, that's the way the thing works. If you wanted to oscillate along the x-axis, what will you replace x with? Anybody? Give it a go. I mean, it's you replace x with x minus a sine omega t. That's all. Simple. You see how it just works so beautifully. And let's try that out. Okay, let's try that out. I don't want all this. Let's try that out. I don't want all this. I'm going to replace x with x minus a sine of I don't have omega, so I'm going to give w. Actually, let me put 2 pi by capital T into t, because then I can right, there you go. See the ball? You can choose your amplitude, your time period, all that. Again, these ranges have to be set very carefully. If the time period goes up, the frequency comes down, right? I suppose that is understood. Amplitude go from 0 to say 5 is my limit. Time will go from 0 to say 10 seconds, and r is the radius of the circle. I can go from 0 to say 2, right, in steps of 1. Okay, so let's try that. Let's try that. Look at the equation. Look at this equation very carefully. What have I done here? If you want, in fact, let me write this. This is x square minus y square is less than or equal to r square. Y is not equal to and less than or equal to, because then it will shade the circle. If I just simply give equal to, it won't shade the circle. It just gives me the border. So I like it shaded because my animation then looks good, right? Oh, by the way, if you put greater than, see what happens. Oh, greater than or equal to, it will shade everything but that, right? You could look at it that way also. So you put less than or equal to, so you get the full ball. And in place of x, I have substituted with x minus a sine omega t. And you play. It may not be very easy. So I'll increase the time period, slow it down, and then you'll see that it's beautifully executing simple harmonic oscillation, right? Between by the way, this a is equal to 1, meaning you're talking about the center of the circle. No? If you want to see, in fact, if you want to see the center, I have to put this with equal to. You can see that the center of the circle will go between -1 and +1. Now, if you increase the amplitude to 2, there you go. It goes from -2 to +2, and it oscillates. This is simple harmonic oscillation, right? It follows all the rest of the rules comes together, right? Very simple. So now you see, in a wave, the particles in a wave don't oscillate when we, at least when we draw the wave, we don't let it oscillate along the x-axis. We let it oscillate along the y-axis. So what should I do? I should replace y with this thing. I should replace y with y minus this. So it will oscillate about the y-axis. So it will oscillate about the y-axis. Okay. So I think it will, this will kind of, now it's a logical step now to move forward and make a full wave, right? Can anybody help me with this? I can give you a first few steps and then we can take it from there, right? Oh, and I forgot something very important to tell you. Very important. Watch. There's a mathematical extension. We wrote that the equation for simple harmonic oscillation is simply y is equal to a sine omega t. But if you write a into sine of kx, what we get is what we call as this is a static wave. This is a static wave, a wave that does not move. It will be just in wavy pattern. See, it is a function of x. So you can just, I can just quickly do that and show you. Let me, in fact, just duplicate this so I can get another. And I will just put y equal to a sine of kx. As I showed you, you just get a wave. You'll just simply get a wave, right? Now, what I want is this. I want this static wave to move along the positive x direction. And what do I do to make any graph to move along the positive x direction? I replace x with x minus vt. So I'm going to do that. Y equal, this is a static wave, a sine of k, right, into x I replace with x minus vt. Okay. Let's simplify and see what we get. A sine of kx minus, oh, actually, let me replace k with 2 pi by lambda. And then I will get is 2 pi by lambda into x minus vt. This is lambda. And keep going. Sine of 2 pi, open the brackets, minus 2 pi minus 2 pi vt by lambda. Ooh, and here's the fun part. What is this? Can someone tell me? Which will, sorry? Yes?
Frequency, it will be frequency.
Correct. So 2 pi x by lambda minus, because we know v is equal to f lambda. So v by lambda is obviously equal to f, which I can write as 1 by t. So I will write this as 2 pi by v by lambda is 1 by t into t. So you see, that's the way. You want to make a static wave move forward in the positive x direction, replace the x with x minus vt. Right? I'm going to show you something that makes no sense at all in physics, just to tell you that mathematics works very logically, because now if I replace in this equation, if I replace y with y minus y vt, what do you think is going to happen? This whole thing is just going to move up, nothing else. There is no wave here. It's just some funny thing. I don't know what it is. Just to tell you that it's logically possible to go step by step. Now we don't want this static wave to move up and down. It makes no sense. Physically, it makes no sense. So instead, I want to replace the x with x minus vt, and so I replace x with x minus vt, and you get your wave. You get your wave. You could now simplify and write it the way that we have already written, because then things become so much easier. Right? So yeah. So now keep this in mind. We will finally come back to this. Keep this in mind. We'll come back to this. Let me clear this up, and we come to the last bit of what I want to tell you. Now, who can help me? I want to make a full wave, right? And you know that, if you take a wave, actually what we call as a full traveling wave, you have many particles at each of these points. Many particles at each of these points. And all of these points are executing simple harmonic oscillation up and down while the whole wave moves forward. Of course, this is called the transverse wave, where the particles move up and down and the wave itself moves forward, right? And I see that I was planning to do it in 1 hour. I've gone beyond that. So I will just quickly tell you how I want to do it. X square plus y square equal to, square equal to r square, right? This is, and I would like to keep this less than or equal to. Then I get the color I want, right? And then this is the first ball. I want this ball. This is one particle in the wave. Now I want another particle in the wave. What will I do? And that particle can't be at the same place. It has to be moved forward. So let me move it forward along the x-axis. I replace the x with x minus a 2. So I moved it forward a little bit. Now I'm going to reduce the size of this thing. Okay, let me move it to 4. Okay, now I want another particle at 8 and then another particle at 12 and another particle at 16. 1, 2, 3, 4, 5. Well, I'll keep going. And I want another particle at 16 and then 20. 20. Right? And another particle at 24. Okay, let me stop here. So what did I do? One particle, look at the equation. I want you to look at the equation. X square plus y square less than or equal to r square. All the other equations are the same, only x is replaced with the offset that we want, the position that we want. Right? Now what do I want to do? I want all of these fellows to execute simple harmonic oscillation, but where? Along the y-axis. So therefore, right? Therefore, actually I should have put the bracket on every y. I will give y is equal to minus a sine of, oh, and now I'm going to put the full 2 pi divided by t into t minus 2 pi divided by, let me call this, instead of I don't have a lambda, so I'm just going to keep it L. And this will be x, and here it will be t, and here it will be t. Okay, this is the full equation, right? And wait, I'm going to replace all. I want all of these balls to, sorry, something, I made an error somewhere. I think I made a mistake. I forgot. Sorry, I forgot. There. I made a mistake somewhere. I'm trying to figure out where. Hold on. Oh, I got the mistake. What am I doing? I'm not changing. I'm only getting that thing to oscillate along the y-axis. So I'm just going to simply put a sine of, I don't need kx because I'm not getting it to move. There are not multiple particles, it's a single particle. And that particle, I want it to oscillate 2 pi by t into t. That's what I want. Okay, that's okay. Now I'm going to copy this. Right? And now you see what happens when I play on t, only that particle is moving. Because why? I haven't changed the this one of the other particles. I have the equation of the other particles. I've only changed the equation of the first particle. The other particles are all there. I'm going to reduce, these will be required 0 to 10. And I'm going to make this rather slow, right? And I'm going to make it from 0 to 10. And I want it to go in the same direction. Right. Now let's look, see the only one of those fellows are moving up, down, and back. up, down, and back. Okay, it's executing simple harmonic oscillation. If you want to see it better, let me increase the amplitude to about 4. Okay, you see that. Great. Now I want the next guy also. I'm going to stop this. I want this fellow also to be replaced. The violet one also has to be replaced. So I'm going to just copy that and paste it here. Right? And then I'll paste it here, and I'll paste it here, and I'll paste it here, and here, and here. And when I play, well, that's not a wave, right? That's a whole bunch of balls bouncing up back and forth. Now, how do we make this a wave? How do we make this a wave? Anybody?
Time delay, sir.
Correct. You want to phase difference, right? You want phase difference, right? So how do you add the phase difference? You want to go inside this, right? You want to go inside. Let me switch off everything else. Let me switch off everything. In fact, wait, how many are there? 1, 2, 3, 4, 5, 6, 7. Let me add one more. Make it 8, even 8. And 24 plus 8 is 20. Okay. I think that's how I'm going to wait. Let me just counter. 1. Wait 1 second. Let me just count how 1, 2, 3, 4, 5, 6, 7, 8. Oh, 9. I want 1. That's what I thought. Need 1. So in order to make a full wavelength, okay, I'll tell you why that. So as you can imagine, in a wave, the first one and the last one will be in a full wave. If you take only a single wave, that is, I'll go back and show you this, that this particular particle, this fellow and this fellow will be absolutely in phase, right? Yeah, the green and this guy, let me change color to blue, will be out of phase. So let's add that phase difference to the equation, right? Let's add the phase difference. So here the phase difference between the first one and this one will be 2 pi. So I'm just going to put minus 2 pi. Is it minus or plus? Minus. Okay. All right. And then, so now if I play, what happens? Well, the first one and the, hold on. Oh, there's no difference. Never mind. Let me switch off everything else so that you can see. Okay. So now you know, let me just rearrange this. It'll be easier. I have the whole thing ready and prepared, but I wanted to go step by step. So hence this delay. Okay. So now you have only the first and the one are in phase. Now the middle one, which was where is it? Is it the one, let's see, the one here at 16 is out of phase. So I want to put that minus pi. And then you play it and you see, look at that. They're absolutely out of phase, right? And then what about the ones in between? Keep adding your phase difference. This is pi. The one between the 0 and pi, the one here must be pi by 2. So I will subtract here, change the phase difference to pi by 2. And I will play that and watch. There you go. There you go. And the one between 0 and 2 pi will be pi by 4. So pi by 4. And I play it. There you go. And then here I want between pi by 2 and pi will be 3 pi by 4. And there you go. There you go. Right. And so on. I'll keep adding all the phase differences. Right. And I will get the full wave. Now I want to stop quickly, but I will show you the final product of what I was doing. Let me close this. Let me take this wave motion. Look at that. So there's a whole lot of things that you can do. So look, I made it all together, and there, look at that. It executes simple harmonic oscillation, and I will keep the wave motion rather slow, right? Each of it has a specific has a phase difference, but one and the other. And if you put the whole thing together, that's what the wave is. It moves forward. right? And the black one, the black line that you see, it's not there. It's only these particles that are actually there. But the visual effect, or rather the transmission of energy, happens in the direction of the black one. That's the thing, right? Now, I can show you a whole lot of other things that that I have done quickly, and then I will, you know, this standing wave. In fact, this I must show you, right? This is from the textbook. Let me open this is the CBSE textbook, and I want to go to page 3. Look at this. This is what this is the CBSE textbook. It shows here, if you look carefully, you have this dotted line wave, which is going in the positive x direction. This other long lined wave, which is going in the negative x direction. And the sum of these two is the blue. And so I made the exact same thing. The only difference is, let me put it side by side so you can see. Right? This is the same. I was trying to do the same thing. The dotted one is dot. So the dotted one goes forward. When I press T, it goes forward, as you can see, right? The dashed one goes back. These are two waves, and when they interfere, you basically just add up the two equations. You got one equation here and the other equation here. See, I call this y1 is this, y2 is this, and then write y is equal to y1 plus y2. I get this, which is what being shown. So if you want to see only the blue one, this is what we call as a standing wave. That it doesn't really move, it just stands where it is and then just goes. What happens inside the what do you say, the organ pipes and so on, standing waves. It's an addition of two waves. Look at that. It's an addition of two waves. So you can't show this in the textbook, which is why they have shown the same thing happening in different timings. Look at that. This is one time, then after some time, then after some time, then after some time, and so on. But you can actually get to see it if you use this, So yeah, so I think that's basically what I wanted to show. I have some other very interesting stuff, but I mean, I will go into that if you have any questions, you can ask. I think I'm done, right? This is basically what I wanted to talk to you about. But just to show you that if you just get logically step by step, and I mean, I had seen in a video once long back that if you want a graph to go in the positive x direction, replace x with x minus vt. And then I started playing with this, and then I asked myself the question, you want a ball to go, you make the circle and you replace x with x minus vt. Well, what about simple harmonic oscillator? I just put it in as the x is x minus a sine omega t, and it just worked. It just worked. So then I painstakingly sat and worked the whole thing out, and I ran this with a couple of I think 2 years. I showed this to the students during the pandemic, yeah, because then we were all online anyway. Of course, I didn't go through these details. I just showed them this is how it happens and so on and so forth. You can have, I have a whole bunch of other things on beats and damped oscillations, and damped oscillations are particularly interesting because you really see the mathematics of it, right? You have a wave, right? It looks like this. I can maybe change the frequency. Oh, by the way, when you put an equation and you put curly brackets, and you can specify the values for which you want to show. So this means that the graph will only show for x values greater than 0, right? If you put less than 0, it will show in the other direction. So you can specify, or if you want through only a specific limit, like say -2 less than x less than 2, then it will show only during that period, nowhere else. Look at that. So these specific, you can make it quite specific. So I will just give it x greater than 0. Sorry, greater than 0. So this is the wave. Now you see what happens, and then you have a multiplication factor, which is your the exponential decay. You multiply the two, what happens? So you want to superimpose this red one with this violet one, and what you get is this. Oh, I'm sorry. What you get is this. Look, if I take that off, look at that. Right? So these, so you can actually show what really goes down. This is the damping factor here. That is and the rest of it is your regular oscillation. So it is confined to fall within that, right? You have beats is one other thing that you can again show here, right? You can add you have one equation, you have wait, 1 second, let me see. Hold on, right? I have to change. There, look at that. So you see, look at, I've put 2 frequencies here, F and G, I called it. So F and G are very close to each other. Can you see? That's when you get the beats. So your cos function confines the sine function here, the sum of the sine function. This is the sum of the 2 waves, and then it is confined by that, and you put that together, you get this. That's your beats. So if you, I think if you play around with this, you'll be able to come up with more. And I think this appeals to once you show it to them, and then you can use a t in your equation and get it to play. I think it kind of makes more sense, right? So yeah, and on a fun note, I also made a smiley face with equations. It was very simple. I think this is a parabola and 3 circles, and you can actually get the smile to frown if you want, right? And you can have this guy, I think you can have this guy be very, happy, or whatever that is. He can look down, he can look up. You see the equation, what I'm doing is I'm just the large circle, I'm just getting it to move up and down. That's it. I can have this guy, I suppose I can have him look to the side, to the other side. And then, then I came to realize that there is a whole world of people who do art with DESMOS, right? And if you look at this, there is something here. Submit this graph to the global math art contests. Yeah, which kind of asks, so if you type DESMOS art competition, and you'll be surprised by what comes. And people just drawing fantastic stuff only with equations. You pick one and you just go in there, and it gives you with the equations and the whole thing. Let's see if it opens. Oh, I don't see anything. Maybe my computer is not fast enough to. There it is. There it is. So you can make folders here in this. Yeah, there are many functions that are involved here. So they can make folders and put them all into folders. So if you keep switching them off one by one, it'll go off. Large building, tiny building, and so on. So if you look at the art contest, you'll see there's one person a few years back who made Vincent van Gogh Starry Night. If you search Vincent van Gogh Starry Night DESMOS, you'll get that with all the equations. I mean, it's so beautiful, right? So yes, I will stop. Thank you. Now, if you have questions, I'm happy to.
Good evening, sir. We have to sign up for this if we have to use this DESMOS?
No, you can use it free of cost. If you sign up, you can save your graphs.
Okay.
That's the.
Okay, sir.
Hello, sir. Maya here.
Hi, Maya.
Sir, I have a question related with stationary waves, though not directly related with.
Sorry, you have a question related to?
Stationary waves.
Yeah.
But not connected to DESMOS per se.
Okay.
This has been nagging me for a long time, and I haven't found a satisfactory answer. So just so that, I mean, this is a forum where a lot of physics teachers are there.
Yeah.
So in case whoever can answer this,
correct,
I'll be glad.
In fact, I'm almost sure I don't know the answer, but go ahead.
No, it's quite probable. It's quite probable that you or one of the people present here might know this. So we teach this in the Bohr model atom, that there was this prediction about stationary waves, that only those orbits are allowed where integral number of wavelength can sit on the stationary orbits. 2 pi r is n lambda. The de Broglie prediction.
Yes.
So there, the concept is similar to that of stationary waves on a string. On a string, it is easy to understand where you have two knife edges, for example. On a node, there is a reflection, and hence they stop progressing and the energy is bound between the two nodes, and hence the formation of stationary waves. But as a strict analogy, what makes the wave reflect back upon itself on a stationary orbit? I'm not able to explain this to students as an analogy. It's just a hand down. Like as the book says, we verbatim repeat it to children. But the question children ask is, what made de Broglie come up with this idea that 2 pi r must be n lambda if it has to be a stationary? So I have not found any explanation for this.
Hi, this is Aparna here. Maya ma'am, hi. I just wanted to reiterate and know if I've got the question right. So is it that you're asking how the electron is restricted within that range? Why doesn't it go higher or lower? Is that your question?
No, ma'am. What I'm trying to ask is, the de Broglie postulate or hypothesis was 2 pi r is n lambda. And using that, he went on to prove that angular momentum is nh by 2 pi, which is Bohr's postulate. And this happened almost 10 years after Bohr's postulates came into existence, or he postulated. So my question is, I mean, children always ask, what made Bohr come up with the postulate? That itself we don't know. How did he hit upon the idea? We don't know. And the next question they ask is, how did de Broglie come up with this proposition that 2 pi r should be n lambda? And the statement in the book is, they are stationary waves, so they must fold back upon themselves, forming stationary waves, as what happens on a string after reflection at a node. That is how stationary waves are formed on a string after reflection. So it's the same story that's happening on this orbit as well. So, but at least on a string, we have knife edges where reflection happens. But on an orbit, which itself is imaginary, how can reflection happen? Or what is it that I'm missing? That is my query.
Aparna?
No, listening to this question, I just got a random thought if it is related to electron in a well where because of the energy, it is restricted within a certain region, like it cannot exist in any other place, but I'm not sure if that's right.
No, I agree with your point. That condition, I agree, but the statement that stationary waves are formed on an orbit, just like how stationary waves are formed on a string, that analogy is what I'm not able to understand this so far. That's my problem.
May I say some things?
Please.
Actually, I don't know the physics level. I won't go to it. I do teach de Broglie and Bohr's theory in chemistry. So from what we do there, from that perspective, I will say is we are using the quantum mechanical principles out there. What Bohr did was apply the quantum theory or to what we say to it. So there it's electron which is behaving like a particle and behaving like a wave. It is that dual behavior which it is showing. So the strings wave, I don't think maybe the book has, I don't know which book or what, I don't know that level. I won't talk about, but when we teach in chemistry, we don't talk about comparing it with a standing wave because electron as such is behaving like a wave, which we get to it.
Ma'am, I'm referring to 12th standard CBSE textbook, NCRT textbook.
Okay, the physics textbook, ma'am.
Yes.
Yeah. Okay, maybe I do teach chemistry, but in chemistry, like this same topic we are teaching, but we don't have the same statements which you are saying. It's quite it's for me also a new thing. So just what I teach in that perspective, I just told you.
Thank you.
So I just spoke to Ani sir. I've asked him. He had some technical difficulty. He wasn't able to fix it. So he'll try and join, he said, and he'll probably give an answer to the question.
Sir, I do have a question. I was trying to do it while you were doing it. How do you decide which phase difference you give the particles? Because I ended up getting a slightly weird, my particles are moving at a different wave than my stated wave.
Yeah, so what you can do is start with the first one, right? Choose, see the position where you want it. The equations, let me just show you this. Let me just show you. Okay, now could you ask your question again? Your question is about where it is positioned or how it is moving?
No, sir. Do you remember at the beginning, all of your balls were moving in phase with each other and you gave them a phase difference?
Correct.
How did you decide what phase difference to give them?
Yeah, so you choose which is the ball that comes at the beginning of the wave. Then, at half the wavelength, quarter of the wavelength, and 1/8 of the wavelength. So you see, if you look at these equations here on the, can you see here, we go from L at X all the way to L minus X minus L being lambda. I'm basically using it for wavelengths. So let me show you that. Hold on.
Oh, no, I understand. So you have 9. Yeah. So you picked your middle one as
correct.
Midway
So,
through the phase.
Yeah. So here I've put it in such a manner that I can change the wavelength of these things also. I started with that, and then so whatever value of wavelength you give at exactly L/2, the phase difference must be pi. At L/4, the phase difference must be pi/2, and so on.
Okay.
That's so if you look at it, there is a relationship between the phase difference and I can't call it path difference, the position difference, right? And that has to be proportional. That's the way you get it, right? So in this particular thing, for instance, see, look, these two are going up together. If you can see these two, one second, just zoom in a little more, right? And if I take the middle one, that will be exactly out of phase, right? And the ones in the middle of those would be like that, and the ones there will be like this. Maybe I should slow this down.
No, sir, I understand. Thank you. I think I just
right. And one thing I wanted to say is that yeah, so if you make it like this, you can change the wavelength there. You can squash it and make it smaller. And this may not make sense, which is why I put this there, so that you kind of get what's going on. So you increase the wavelength, decrease the wavelength. Okay.
And Sir Mani sir is here now.
Hello, Mani sir, can you turn your video on?
Oh, sure.
Yeah, we can hear you now. We can hear you. Welcome, sir.
Yeah, but it is better that somebody puts it in the chat mode for me. Thank you. Thank you, Anand.
Yeah. Maya ma'am, do you mind typing your question down? But we will wait. In the meantime, we'll take some other questions.
Yeah, I'll try, sir.
Yeah. So, sir, Maya ma'am asked a question, and I think it kind of went above all our heads. So we thought we will swoop in and ask the expert.
I was watching a few things, and in between I got disturbed, but I had to come back, and I noticed you have done something very good. You've also tried to give a definition of a general wave. Okay, that you have taken different functions. The way I like to do it is this, that I just write f of x minus vt. F is any function, doesn't matter whether it is sine, cosine, or sine squared, whatever be the function. I will just write it as f x minus vt. This f bracket x minus vt bracket is the most general wave I can write, traveling, if v is positive, traveling along from left to right.
Correct. Along the positive x direction.
Yeah. And the simple way to see it is this. If I change x by x plus some constant c or constant a, add x going to x plus a or c, okay, it doesn't matter. And t, no, don't write t there. Remove t from there. Write t below x. Sure. To the left, t going to arrow. Arrow t plus v by a. No, v by, wait a minute, what should I say? A by vt. Please rub v. A divided by v.
A divided by v. Correct.
Okay, that's it. Now v. Now substitute it at that place. What do you get? You see.
Substitute
x plus a. So I get x plus a. Write down x plus a. And then minus, put a bracket. V plus t plus v bracket.
V bracket.
Another bracket. T plus a by v. Now open the brackets and close and see what happens. So you get back x minus vt.
Right.
So what do you interpret it as? That at a time a plus a divided by later, the wave has moved to x from x to x plus a because the function has not changed.
Correct. Correct.
And this is generally true for any function.
Right.
So supposing I have a temperature wave coming, or a density wave, or a water wave. This is the most general one because all the temperature wave need not be a sine wave. Usually is not.
Thank you. Sir, can you check the chat box? I think.
Okay, here, stationary wave on string, we know a reflection happens at the rigid boundary like sonometer. That is correct. That statement is correct. I agree. So what is the question here? Or is it just a confirmation of this statement?
No, she's still typing. I think she's still typing.
Okay, fine.
Sir, may I read out?
Please, slowly, because I am hard of hearing and my speaker system is not the best in the world. That's why I wanted in the chat mode.
Sir, so sonometer, the production of stationary waves, we understand with a little bit of difficulty. It's not an easy concept, but yes, we do understand. But the same analogy seems like is applicable for stationary waves for a orbiting electron as well, as proposed by de Broglie.
In the last, what is the last word you said? Electron as well?
The orbiting electron in a stationary orbit,
yes,
as
orbit,
proposed
right.
by de Broglie.
Correct.
Said, I mean, Bohr first proposed that L is nh by 2 pi. MV, angular momentum is quantized. Only those orbits are allowed where angular momentum is quantized. So the NCERT textbook and all other physics textbooks say later, about 10 years ahead, de Broglie proposed that stationary orbits are those orbits in which electron waves are like stationary waves, such that 2 pi r is n lambda.
Yes, that statement I have read. Perhaps I've also written it down when I participated in NCERT. I don't remember. Okay.
So my doubt is, if they are stationary waves, what makes them reflect upon themselves? Where is the reflection happening? I have struggled to explain this to students.
Okay, now this brings us to a very deep mathematical reason. When you take a line or a circle, there is a drastic difference. In a line, if I take a line segment, there is an end, 2 ends. But in a circle, there is no end. That is the reason why stationary wave there has to be defined differently. Because supposing this was not there, then if I get a maxima at one point, when I go around, and if 2 pi r is not equal to n lambda, but n plus half lambda, n lambda plus lambda by 2, I will again get a destructive part. So when they all add up, going round and round, they will just add up to 0. Am I clear or no?
No, the statement makes sense, but I am not able to wrap my head around the fact that they are reflecting, even though there is no rigid boundary.
That's correct. So there is the reflection is not in terms of a coming back in the same path, but going around and coming to the same point. What is important is it should come back to the same point. How it came back, whether through a rigid boundary or whether making some path and coming back, doesn't matter. When it comes back to that place, I have to add the two waves. Like, for example, if I had a canal, circular canal, if I send a wave from one side, when it goes and comes back, and let's assume the wave is such that it doesn't decay, then again, if one of them was positive and then the other came as negative, the whole thing will collapse. Okay, if I had a circular canal with water.
Right.
All right. But there is a little bit more to it than that. And let me tell you that. You use the word stationary, and the way it's here. There in the quantum mechanics count, stationarity means something more. It means that as time develops, the system does not change. Okay?
Right.
It's defined as stationary state, isn't it?
That's a stationary state. So here, the wave which is going around the orbit is the one which is a stationary state of the hydrogen atom, if we are talking about one electron system.
Can we think of it like this? The energy in that level is fixed, and that's what Bohr meant by quantization.
I must say this confusion remains with us for a long time. I was also, when I studied it, even when I did my BSc, as usual, we memorized it and then wrote it. But only when I learned quantum mechanics properly, the whole thing fell into place.
Okay, thank you.
The half explanation takes you only up to a point, but then it cannot be ignored because it is partly true. And that is the beginning of understanding. That's how Bohr's original papers were all using that argument, was what they all did at that time.
Thank you, sir. Thank you, Maya ma'am, for asking the question.
Thank you.
This is a difficult question.
I have never been able to explain this to class because I've never understood this myself. So thank you. I at least have the canal analogy now. So thank you, sir.
Yeah, I think that should work.
Thank you, sir.
You're welcome.
Anyone else? Anything else? Otherwise, we'll close. Thank you for all for joining, by the way. I think then we'll call it a day. Thank you for joining. And I think like I said in the beginning, if all of you have teaching learning ideas that you would like to share, please get in touch with us. We'll be more than happy to arrange a session like this. Of course, unfortunately, it can happen only on Saturdays or Sundays. I mean, for me, Saturdays and Sundays are free, but I think you being most of you now in the school, you'll probably find only Sundays free. And we will also take up theory and all as we go ahead. Thank you, all of you, for joining. We are very glad that you came again. You took the Sunday off, so that means a lot. Thank you.